Hello everyone. So I'm just going to record this lecture and you can watch it later on. So just to revise, in the earlier classes, we studied this body stability criteria, which states that a feedback control system is unstable if the amplitude ratio of the corresponding open loop transfer function is greater than 1 at phase crossover frequency. That is so this body stability criteria states that at phase crossover frequency the system will be unstable if amplitude ratio is greater than 1. And we define this phase crossover frequency as the frequency where the phase shift is equal to minus 180 degrees, that is minus pi. Then other critical frequency, we define it as gain crossover frequency, and that is the frequency at which the amplitude ratio is 1. That is, if amplitude ratio equal to 1, the omega at which amplitude ratio equal to 1 is our gain crossover frequency. Now, the stability criteria, according to this body stability criteria, is that if at the phase crossover frequency, the corresponding log modulus, so basically this is the amplitude ratio, that is the if amplitude ratio is less than 1, that implies that the feedback is stable. These are the Bode plots. So the first one shows us the relation between the amplitude ratio versus the frequency omega, and the second is the phase lag versus omega. So we define that if the phase crossover frequency is the frequency at which the phase lag is minus 180 degree. So basically over here the phase lag is minus 180 degree, and this is our phase crossover frequency. And at this point our amplitude ratio should be less than 1 for the system to be stable. So this is what our body stability criterion states. Similarly, we define this gain margin and phase margin. So the gain margin is basically, you can consider this margin as the safety factor. So the gain margin, we define it as the inverse of the amplitude ratio. So over here, X is our amplitude ratio at this phase crossover frequency. So gain margin, you can write it as 1 upon amplitude ratio. Similarly, we define this safety factor related to this phase lag, and we call it as phase margin. So that is basically 180 degree plus theta, where theta is given by the argument of the angle given by our transfer function at this gain crossover frequency. Basically the phase lag of the transfer function at gain crossover frequency. And using this Bode stability criteria, we can conclude on these 3 points. So if both the gain margin and phase margin are positive, then the control system is stable. If the gain margin and phase margin are equal to 0, then the control system is marginally stable. And if the gain margin and the phase margin are negative or are negative, then the control system is unstable. So if both are positive, it is stable. If both are 0, it is marginally stable. And if both or one of them is negative, then the system is unstable. So in earlier class, we also covered these processes with inverse response. So basically, we say that our process is giving an inverse response if it's first response in another direction, and ultimately it will become stable at some other opposite direction. And the general form of this process with inverse response, we can write it using this general form of the output response, that is y of s. You can write it using this way. And one of the characteristics of this inverse response is the system should be having a positive zero. So zeros are defined as the roots of the numerator. So if we are having transfer function as g of s is equal to numerator upon denominator, then the roots of the numerators are called as, we term it as 0, and they should be greater than 0. At least one of the roots should be greater than 0 for the system to exhibit inverse response. So now we will be looking on to this instrumentation. So we will be covering this pneumatic valve in this lecture. Then various characteristics of the different type of pneumatic valves based on the flow output. Then look on the diagrams, the response or the characteristics of the pneumatic valves. And then solve questions related to this instrumentation, that is pneumatic valve. We will be also covering few general questions related to, again, this response given and transfer function. So this question is related to that. Then this question is related to this controller. So what are the effects of introducing different kind of control actions such as integral control action? This question will cover that. Then this question covers the direct response and the direct control action and reverse control action. So we'll be covering a bit of theory on this also. So this is our plan for today's session. So first we will discuss about this pneumatic valve. So until now, what all we have done is we have modeled the process, that is process modeling. Then we perform the stability analysis. Now, in order to take the control action based on this stability analysis to make the system stable, we need this instrumentation. So one kind of instrumentation will measure the output or the measured variable, and then that needs to be controlled using some action. And most commonly, we used this pneumatic valves to control to manipulate the controlled variable. So this is what pneumatic valves does. So pneumatic valves are basically air-operated valves that are used for regulating the fluid flow through a pipeline. So let's say if I'm having a pipeline and a fluid is flowing through it. Now, our main objective is to control the flow of the liquid or whatever gas is passing through this fluid. So that is our main objective, to control this. So for that, we will be using a pneumatic valve. And this set point to the pneumatic valve will be given by measuring some physical quantity. So let's say if I'm having a temperature indicator over here and this fluid is steam. If the temperature rises, and if I want to decrease the temperature, I should decrease the flow of the steam. That is, I should be closing this pneumatic valve. So that is the main function of pneumatic valve. So in order for the pneumatic valve to function, we provide the instrument air in order to control the output of the valve. So basically this varying air pressure between 3 to 15 psig, that is pound per square inch gauge pressure, is used as an actuating signal for pneumatic valves. So usually a control signal is generated and transmitted in electrical form from the controller. So what will controller do is controller will give the signal in the form of this, current, that is I, and ultimately it will be converted into this pressure P. So that is, we'll be changing the air pressure of this instrumenter, and on the basis of that, the valve will get open or closed. So this schematic gives us a better idea. So let's say if I increase the pressure of the air, so that is if it is maximum, that is 15 psig, then in such a scenario, this stem will move downwards, and once it moves downwards, the valve will close and the fluid output will be 0. Now, similarly, so in this kind of valve, you can see that if I'm using this air pressure, then the valve is getting closed. That is air to close. So such a kind of valve is known as air to close valve. Now, in this valve, you can see that if I'm using this air pressure, then the valve stem will move downwards and the valve will get open. And in absence of any pressure, due to this spring action, the valve will get closed. So in order to open the valve, we need to provide air pressure. So such a kind of valve is known as air to open a valve. So we can change the flow by changing the air pressure, and that air pressure is changed in this range of 3 to 15 psig. And ultimately this signal, that the 3 to 15 psig, is transmitted by using this I2P converter. So what will I2P converter do is, a current to pressure converter converts an analog signal 4 to 20 milliampere to a proportional linear pneumatic output. So basically I2P converter will convert this 4 to 20 milliampere current into 3 to 15 psig. So its purpose is to translate the analog output from a controller into precise repeatable pressure value to control pneumatic actuators, pneumatic valves, dampers, or wheel. Basically, in order to control, the controller will be provided current input, and that basically this control valve, it will be converted into this pressure valve so that this controller can take that air pressure. Now, so if a fluid is passing through the pipe, so if we are considering, let's say 2 point, then the pressure drop across the pipe, let's just take it at delta P, then the flow through the pipe can be written using this equation. So the flow through the pipe will be proportional, will be equal to the valve coefficient CV. Now Fx are the flow characteristic curve of the valve upon into under root of delta P upon rho. Rho is the density of the fluid passing and delta P is the pressure drop. So this flow characteristics defines that how much amount of fluid will be passing through my valve. So basically that f of x is known as flow characteristic curves, and it depends on the shape of the plug of the valve. So over here we can see that the valve can be of different shape. So if it is of this form, we call it a square root. If it is of this conical form, then we call it as linear valve. Then such a flat kind of valve having a trapezoid kind of cross section, we call it as quick opening. Then such a kind of valve is known as a hyperbolic and equal percentage valve. So basically, if I'm using such a kind of valve, then the valve characteristics are linear in nature. So the equation relating the flow characteristic valve with the stem position is given by, for each of that valve is given by this equation. So over here, x is the stem position. So let's see if I'm having such a valve. So x basically denotes the stem position. So if x equal to 0, that implies the valve. So basically x, the value of x will vary from 0 to 1. So this means that the valve is fully open, and 1 means the valve is fully closed, that the valve position is is touching the seat. So on the basis of that, we are having this linear characteristics wall given by f of x is equal to x. Then we have this square root wall where f of x is equal to under root of x. Then equal percentage valves are given by alpha raised to x minus 1. Then hyperbolic valve and peak opening valve. So if we see the flow capacity characteristics versus the stem position, so basically this value of x, then we will get such a kind of graph. So the first one is a quick opening graph. So as the name suggests, it is a quick opening. So with very minimal change in the value of x, the flow will increase significantly. That is, it will quickly open with respect to and the flow will quickly increase. So this one is the quick opening valve. Then over here, the green one is the square root valve. The blue one is the linear valve. So that is the flow capacity characteristics will vary linearly with the stem position. That is f of x will vary linearly with the stem position. Then the red one is the equal percentage valve. And this light blue one, we can call it as hyperbolic valve. So let's derive few of these equations. So if we are having a so the linear valve will mean that df by dx, where f you can call it as flow upon maximum flow, and x you can call it the minimum stem position upon maximum stem position. So in linear valve, that is the flow will vary linearly with x. That is delta f will vary linearly with x. So we can say that the slope will remain constant. So this is how we define this linear valve, and if we integrate it, we can write that f is equal to alpha x. So that is basically how we get this equation, f of x is equal to x. So over here the slope is 1, and in our case the slope will be alpha, but they will be varying linearly. The second kind of valve, we can call it as equal percentage valve. So in equal percentage valve, what will happen that df upon dx will be proportional to the f, that is beta f. From this equation, we can write that df upon f is equal to beta dx. That is, the percentage change in the f is equal to the change in the stem position, that is dx. So that is why we say that equal percentage valve. Now if I integrate this equation, I will be getting ln f is equal to beta x. Let's say at x will vary from 0 to x, and at x equal to 0 the flow is f naught, and at x we have the flow as f. So we can write this as ln of f upon f naught is equal to beta x. So from here we will be getting f is equal to f naught e raised to beta x. So this is one characteristics curve of this equal percentage valve. We can further simplify this. So f is equal to f naught e raised to beta x. Now let's say if the valve is fully, if at x equal to 1, that is, let's say if a valve is fully open, okay, then the flow will be maximum. Since the flow will be maximum, the ratio f upon f max will be 1. That is why we write this as this ratio of the flow as for 1. So using that, we will be getting 1 is equal to F naught e raised to beta. So we get the value of beta as ln of 1 upon F naught. Now we can replace the value of beta over here, and we will be getting F is equal to F naught e raised to x ln of 1 upon F naught. So this we can also write this as ln of F naught raised to minus x. That can be further simplified as, so this term we can write it as, since this is e raised to log to the base of e f naught raised to minus x, so it will simply become f naught raised to minus x. So this is f naught raised to 1 minus x. Let's just consider this. If f naught is equal to 1 upon alpha, then we can write f is equal to alpha raised to x minus 1. So this is the equation that we will be using in the further numericals. So basically we derive this equation also, f of x is equal to alpha raised to x minus 1. Now let's take a look on the two of the numericals related to this. So the first numerical is the flow of water when equal percentage valve is 900 liter per hour at 300% at 30% opening and 1080 liter per hour at 35% opening. Assume that the pressure drop across the valve remains constant. The flow rate in liter per hour through the valve at 45% opening is dash. So let's take a look on the video solution. Question number 52 of GATE 2020 chemical engineering paper related to the subject of process control and instrumentation. The question is, flow of water through an equal percentage valve is 900 liter per hour at 30% opening and 1080 liter per hour at 35% opening. Assume that the pressure drop across the valve remains constant. The flow rate in liter per hour through the valve at 45% opening is dash. So first of all, in this given question, we have been given an equal percentage valve. So if we have to draw this characteristics of this equal percentage valve, we can draw it like this. So let's say if x is my valve opening, that is how much percentage of the valve is being open. Let's say from 0 to 1, where 1 means the valve is 100% opening. Then the fraction of the flow passing through, or the flow capacity, we can call that is f of x. We can plot it as in such a manner. And this flow characteristic, that is the relationship between f of x and x, we can write it by this equation. F of x is equal to alpha raised to x minus 1, where alpha is the constant dependent on the flow. So we'll be using this correlation to find the flow rate at any given valve opening. So in the question, we have been given that if flow rate, if F1 is 900 liter per hour, then the valve opening was 30%, that is 0.3. And at X2, that is 35% opening, the flow rate was 1080 liter per hour. That is, we can write this as now in the given question we have been asked the flow rate at 45% opening, that is at F3 dash so we can use this correlation where F is the, you can say, the ratio to the maximum flow and X is the valve opening. So let's put these values in this equation. So if we have to write in terms of this F2 and F1, we can write F2 upon F1 is equal to alpha raised to x2 minus 1 upon alpha raised to x1 minus 1. So F2 we have been given as 1080 upon F1 is 900. Alpha raised to, you can write it as x2 minus x1 minus of x1 plus x1, that is alpha x2 minus x1. Now x2 is 0.35 and x1 is 0.3, that will become alpha raised to 0.35 minus of 0.3 is equal to alpha raised to 0.05 is equal to 1080 upon 900. Now to find the value of alpha, we can take log of this and it will become ln of 1080 divided by 900 will be 1.2 equal to 0.05 times of ln of alpha. That is, the value of ln of alpha will be getting as ln of 1.2 will be 0.1823 divided by 0.05. So that is 3.64. So we will be using this value for our next case, in which we have been asked to find the flow rate at this 45% opening. So the F3 is unknown. Let's take this F2. So F2 is 1080 is equal to, you can write it as alpha raised to x3 minus 1 upon alpha raised to x2 minus 1. That can be written as alpha raised to x3 minus 1 minus of x2 minus plus 1. So from here we will be getting F3 is equal to 1080 into alpha raised to x3 minus x2 x3 is 0.45 and x2 is 0.35. So that is, we can write this as alpha raised to 0.1. Now we need to take log of this to find the value of, no, so from over here we can simply calculate the value of alpha and put it here. So this will give us value of alpha as 38.09. So 1080 into 38.09 raised to 0.1. So it will be 1.43 into 1080. 38.09 is to. So this will, you can approximately write this as F3 is equal to 1555. So the final answer, that is the flow rate through the valve at 45% opening, we can write it as 1555. So in this question, we looked upon how to use this correlation. So we were given an equal percentage valve. We used this correlation, that is F is equal to alpha raised to x minus 1. Basically, this comes from the correlation F is equal to F naught e raised to beta x. From this, we get this correlation, and we use this equation to find the flow rate at any given valve opening. So for any given x, we can find the value of flow rate once we have this alpha. In order to find the value of alpha, we were given these two different scenarios, this first and second. Now, let's take a look on this question. So this is question number 45 from GATE 2013. So in this question, we have been given that a control valve with a turn down ratio of 50 follows equal percentage characteristics. The flow rate of liquid through the valve at 40% stem position is 1 meter cube per hour. What will be the flow rate in meter cube per hour at 50% stem position if the pressure drop across the valve remains unchanged? So over here, we have been given a turn down ratio. Few values of F and X, and given X is equal to 0.5, we have to find the value of F. So let's take a look on the video solution, in which we will also see how this turn down ratio is defined and how we will use that turn down ratio in order to find the flow rate at this given valve. So this is question number 45 of 2030. So let the video load. We are solving question number 45 from GATE 2013 Chemical Engineering paper. The question is related to the subject of process control and instrumentation. A control valve with a turn down ratio of 50 follows equal percentage characteristics. The flow rate of a liquid through the valve at 40% stem position is 1 meter cube per hour. What will be the flow rate in meter cube per hour at 50% stem position if the pressure drop across the valve remains unchanged? Answer up to two digits. So first of all, in the given question, we have been provided an equal percentage characteristic valve. So this means that the flow characteristics of the valve will be governed by the equation F is equal to F naught e raised to beta x, where F we define it as the flow at this valve opening of x upon the maximum flow possible through the valve, that is Q upon Q max. Similarly, F naught we can write it as this initial flow on the maximum flow will remain same e raised to beta x. So that is, we can, in terms of the flow rate through the valve, we can write this as Q is equal to Q naught e raised to beta x. The other thing we have been given is a turn down ratio of 50. Let us denote this turn down ratio by T, and it is given as 50. So turn down ratio is defined as the ratio of the maximum flow possible through the valve upon the minimum flow, that is Q max upon Q minimum. So this maximum flow will occur when the valve is 100% open. That means when x is equal to 1. Similarly, the minimum flow will occur when the valve is 100% closed, that is, it is fully closed, that is x equal to 0. So we can replace the value of x in this equation and put and find the value of the constant beta using that. So we will be putting, for finding the maximum flow, let us put x equal to 1 in this equation. So it will become Q naught e raised to beta 1. For x equal to 0, it will become e raised to beta raised to 0. So that is 50 will be equal to e raised to beta. This will be equal to 1. The value of beta can be found out by taking the natural log on both the sides. So that will be beta is equal to ln of 50. This will come around 3.912. Now we have been given these two different scenarios, that is the flow rate of the liquid through the valve at 40% stamp position is 1 meter cube per hour. That is, let us consider that case 1. So Q1 is equal to 1 meter cube per hour at x equal to 0.4. And for case 2, Q2 we have to find, and the valve opening is, the stamp position is 50%, that is at x equal to 0.5. And we found that beta was 3.912. Now we can straight away use this relation Q is equal to Q naught e raised to beta x. Now using the information from case 2 and case 1, we can write this as Q2 upon Q1 is equal to Q naught e raised to beta x2 upon Q naught e raised to beta x1. So this will get cancelled out, and we will be having Q2 is equal to Q1 e raised to beta x2 minus x1. So Q1 we have been given as 1 into e raised to 3.912. x2 is 0.5 and x1 is 0.4, that is x2 minus x1 will be 0.5 minus 0.4, that is 0.1. So Q2 will be equal to e raised to 0.3912. So you can calculate this and it will come around 1.478. So the flow rate when the valve opening is 50%, it will be 1.478 meter cube per hour. So the final answer, that is up to 2 digits, we will report it as 1.48. We looked on this question where we define this turn down ratio, and using that turn down ratio we find the value of the beta. We find the value of this constant beta, and once we have this value of beta, we simply use this equation to find the flow passing through the valve. Now let's take last question for the day. So in this question we have been given 4 different transfer function, and the question states that which one of the following transfer function upon a unit step change in disturbance at t equal to 0 will show a stable time domain response with negative initial slope. So let's take a look on the video solution. We are solving question number 60 of GATE 2015 camp. This question is related to process control and instrumentation. Which one of the following transfer functions upon a unit step change in disturbance at t equal to 0 will show a stable time domain response with a negative initial slope, that is slope at time t equal to 0. So in this question, corresponding to these 4 different transfer function, we have to find that the for which of these following time domain response we will be having a negative initial slope. So the transfer functions, we can write it as output upon input, that is g of s is equal to y of s upon x of s. In this given question, we have been given a unit step change, that is x of s will be 1 upon s. So the response in s domain, we can write it as y of s is equal to g of s into x of s. So this will become g of s upon s. Now we have to find the slope in time domain. So that is which of the following will show a stable time domain response with a negative initial slope. So in order to find the slope, we can write it the slope at any given time. We can write it as slope at time t. Let's just call it as m. It will be equal to the response in time domain, derivative of the response in time domain, that is dy t upon dt. Now we have to find the value of dy t upon dt and put the value of time t equal to 0, and then find for which of the following transfer function we will be having a negative initial slope, that is for which of the following transfer function m will be less than 0. So if we take the Laplace transform of this derivative, we can write this as dy t upon dt. So this will be, if the derivative of y of t is y of s, no, if the Laplace transform of y of t is y of s, then we can write this as s ys minus y of 0. Now this y of 0, we can find it using the initial value theorem, that is limit s tends to 0 s into ys. So now y of s you can obtain from this equation, and for each of these cases we will be having this y of 0 as is equal to 0. So that is, so this will, the Laplace transform of the derivative will become simply sys. Now since we have to find this term dy upon dt, it will become dy t upon dt is equal to L inverse of s ys. Now ys we are having it as g of s upon s, so it is, will simply become sys into g of s upon s. So that is the Laplace inverse of the given transfer function. So we found out that the slope of the response of this transfer function at any given time, that is mt will be the inverse of the transfer function. Now, if you take a look on each of these transfer function, they are having a general form of, let's say, the one is in each of these transfer function, that is 1 upon s plus a. Let's just call it as plus. So over here we are having minus, plus, plus, plus. So let's just call it as plus n times of p s plus b. So for first case, the p will be minus 2, a will be 1, b will be 4. In each of these cases, a will be 1 and b will be 4. And the value of p will be changing from minus 2 or 2 depending on the transfer function. So in order to find the inverse Laplace transform of this, let's just find it. L inverse of g of s is equal to Laplace inverse of 1 upon s plus a plus s plus b. So this will be equal to, first of all, the Laplace inverse of 1 upon s plus a will become e raised to minus of at. So that is, we can write it as e raised to minus at plus p will get common, and 1 upon s plus b will be e raised to minus of bt. So ultimately this is our derivative. Now we have to find the slope, the initial slope, that is at time t equal to 0. That is at t equal to 0. We can find the derivative as e raised to minus of a0 plus p e raised to minus of b into 0. So this will be equal to e raised to 0, that is 1, plus p into 1. So the slope we found out to be 1 plus p. Now for transfer function given by this equation, the slope will become 1 plus p, and the value of p is minus 2, that is 1 minus 2 is equal to minus 1. So over here we are getting a negative initial slope. Now let's just verify for other cases. For b, we are having p equal to 2, and in each of these cases for b, c and d, the value of p is 2. So the slope in each of these cases will be 1 plus 2 is equal to 3. That is for b, c and d, the slope will be 3. That is a positive initial slope. And in the given question, we have to find the transfer function which gives a negative initial slope. That is the first transfer function, that's option A, will be the final answer. So from the given options, we can select this option A as the correct one. So we discussed on this question where we had to find the transfer function for which the response gives us a negative initial slope. So for that, we had to calculate this slope, that is dyt by dt, and we found out how we can find this using inverse Laplace transform. So this was all for today's class. So from next class onwards, we will most probably be starting with the fluid mechanics subject. Thank you, everyone.